Hello and welcome to this introduction to successor feature representations. They are a transfer learning method for reinforcement learning that I, Chris, and my colleague Xavier investigated. Let's start with our problem setting. In transfer learning, the goal is to transfer knowledge from tasks that we have previously learned to a new task. Consider, for example, this environment where an agent has to navigate from its start state S to a goal state, while collecting objects, here circles, triangles, or rectangles. In the first task, for example, circles receive a high reward, and the agent learns over time this red policy. Then we change to task 2, where triangles are preferred and the agent learns the green policy. In task 3, rectangles are preferred. So now for our new task 4, the goal is actually to collect triangles and rectangles. And we would like to reuse the policies of our previous learned tasks that are similar, here task 2 and 3. So in this case, the agent might directly start reusing the green policy, which collects the 2 green triangles, and then switching to the blue policy, which collects these rectangles. As a result, by reusing these policies, we start learning with a good initial behavior, which improves our overall learning performance. So how do we transfer policies? The idea here is to store the policy of each learned previous task pj, and then given a new task with reward function r, to re-evaluate them by computing the expected return, the q values, the policy would result in if used in this new task. By this, we can use the policy that has the highest expected return. So how can we re-evaluate existing policies for a new reward function? We do this by learning a special formulation of the Q function for each task, which differentiates between dynamics and rewards. Dynamics are what I will see when I use this policy. Here, which objects will I collect when using the policy? Having this, we can compute the value of the policy given a reward function that tells us how to evaluate the collected objects. One such approach are successor features introduced by Barreto et al. Here we assume that rewards are linearly composed of a feature vector phi and a reward vector w. In our example, the features are a binary vector telling if the agent collects a certain object type. And the weights are the rewards for collecting it. Calculating the dot product between the both results then in the reward. Successor features use this linear reward assumption to disassociate dynamics and rewards. If we look at the Q function and replace our rewards at each time step with our linear assumption, we can see that the weight vector is constant at each time step. Thus, we can remove it from the sum over steps, leaving only the discounted feature vectors, which we define as psi. Given psi for a certain policy, we can now compute the Q values for any reward weight vector w by computing the dot product. But this approach has a problem, namely the assumption of the linear relation between features and reward weights, which can only directly represent certain reward functions. Take, for example, this environment where an agent drives in a 2D plane. It has 3 markers, and the features are the distance of the agent to them. Here, the reward function is a combination of Gaussians that encode preferred distances of the agent to each marker. We can see here, for example, a reward function where black areas represent high rewards. Using the successor feature approach in this example is not successful, as the Gaussian rewards cannot be appropriately represented with a linear combination of weights and features. So as a result, the successor feature approach in blue has a lower performance compared to Q-learning that does not use transfer learning between tasks. Our goal now is to allow direct transfer between tasks, where the reward function can be of any general form. To achieve this, we propose the successor feature representation, which is a slight reformulation of the successor representation. If we look at the Q function, we see that if we use features as input to our reward function, at each step we have to integrate over features and multiply the probability of seeing a certain feature at time step t plus k with the reward for it. And again, the reward here is constant for each time step and can be removed from the sum over steps. Thus leaves us with the successor feature representation, which we indicate with Xi. So the successor feature representation is the discounted sum over the probability of seeing a certain feature in future time steps. Given the Xi function and any general reward function, we can now compute the Q values for it. In the case of discrete features, this integral can be replaced with a finite sum, and in the case of continuous features, we can discretize the feature space, for which the integral also becomes a sum. And the Xi function itself can be learned with standard temporal difference methods similar to Q-learning. If we use our approach now in an environment with discrete features, similar to the previous object collection environment, but with slightly more complex features that allow us to have general reward functions, we can see that our approach outperforms the classical successor feature method. We can also see that with increasing nonlinearity of the reward functions, here shown by the increasing error of a linear model which tries to approximate them, the classical successor feature approach behaves worse and worse compared to our new approach. Interestingly, even for reward functions that can be linearly composed, the new successor feature representation approach outperforms the classical successor feature method. And going back to our environment with the Gaussian reward functions, we can now see that our new approach in orange here, can be used for transfer. In summary, our paper introduces the successor feature representation for policy transfer between tasks with general reward functions. We provide several experiments that evaluate linear and general reward functions with discrete and continuous features, and also with learned or given features and reward functions. On the theoretical side, we prove the convergence of the successor feature representation algorithm to the optimal policy, and we show a lower bound on its performance. With this, we want to say thank you for your interest. Please check out our paper for more details, and you can also find the source code of our experiments online. And feel free to contact us if you have any questions. Bye.